Everyone, in this video I am going to explain about sum of subsets from the given set as well as Hamiltonian graph, then graph coloring using backtracking method. Already we discussed about backtracking method in the beginning of this module. Backtracking is a method which is used to solve a problem. First, we will find out the solution. Then if the solution is not suitable for a problem, then we have to go back. Again, we have to trace the solution to find out the appropriate solution for a problem. So in this occasion, there is a chance for more than one solution for a given problem. In the previous cases, that is a greedy approach as well as dynamic programming, we will find only one optimal solution, whereas in backtracking we will consider all the possible solution for a given problem. That is the main aim of this backtracking method. So now let us discuss about the sum of subset of the elements. So the problem is to find a subset of a given set. Let S is equal to S1, S2, etc. Sn of n positive integer, where the sum is equivalent to a particular positive integer value d. So here observation is it is convenient to sort the set of sets element in the increasing order. That is, the first element should be less than the second element. Third element should be greater than second element, fourth element should be greater than third element, and so on. And each set of solution which should not need to be necessarily of the fixed size. It can be anything. For example, consider the example S is equal to 3, 5, 6, 7 and D is equal to 15, which means that from the set 3, 5, 6, 7, I have to pick some element. When I sum up all the elements, the result should be 15. So that's what I have taken 3, the 5 and 7. 3 plus 5, 8, 8 plus 7 is 15. So how I am going to solve this problem means by using state space tree. So by using state space tree, I am going to solve this. So how I am going to solve this problem using state space tree means, first I will consider 3. If I am considering 3, then I have to consider 5 also. So 3 plus 5, it will be 8. If I consider 6, then 8 plus 6 will be 14. Then I cannot consider 7. So in this case, I have to consider 7. I should have to ignore 6. So 3 plus 5 plus 7, it will give the result as 15. Next one is Hamiltonian circuit problem. The problem is concerned about finding a Hamiltonian circuit in the given graph. Hamiltonian circuit is defined as a cycle which passes all the vertices of the graph exactly once, except the starting and ending vertices, that is the same vertex. If the starting vertex as well as the ending vertex is the same, then according to the Hamiltonian methodology, it should not visit the particular vertex. So the remaining all the vertex, it need to visit at least once. So consider this example. There are 6 vertices are available, A, B, C, D, E, F. So I am going to draw the state space tree for this. First A, then A is the starting vertex, then A to B, next one, from B to C, then C to D, D to E, E to F, dead end. From C we can also reach E, B, F. Then from B we can also reach F, then E, then C, then D, then E, then A. So that is the solution. Because as I said before, it need the starting as well as ending vertex should be the same. That's what I'll repeat once again. Starting vertex A, then A to B one path, then from B we can have 2 paths. One is towards C, another one is towards F. If it is C, then from C again I have 2 paths. One is D, another one is E. From D I can reach E, then F. From E I can reach D and F. From B I can reach F, then E, then C, then D, then A. I have to visit all the vertices of a given graph. Then at last the starting vertex as well as the ending vertex should be the same. This is the main concept of this Hamiltonian graph. Next one is coloring map. Let G be a graph and M be a given positive integer. If we want to discover whether the nodes of G can be colored in such a way that node 2 adjacent part should have the same color. In this given diagram, 1 and 2 are the adjacent, so 1 and 2 should not have the same color. 5 and 4 are the adjacent, so 5 and 4 should not have the same color. This is the concept, and here consider this example, how it's happening. I'll explain you using this state space tree. So first, the basic colors are RGB, red, green, blue. So first I'll take red, then in the second level of the state space tree, green. Third level of the state space tree is first level red, second level green. So RG, third level blue. So RGB, red, green, blue. Fourth level red, green, blue, yellow. Then in the fifth level we will get the solution RGBY. So red, green, blue, yellow. So these are the solution for a given problem. Now consider this. Now the map can be colored as followed: red color, green color, blue color, yellow color. There are 4 different colors have been chosen. Look it into it. First, red color has been marked not in the adjacent 2 parts. 1 and 5 has been colored with red. Second part is colored with green. Third part is colored with blue. Fourth part is colored with yellow. So at last we can conclude that 3 things on behalf of backtracking need to be imposed. One is, it is typically applied to difficult combinatorial problems for which no efficient algorithm for finding except solution possibly exists. Backtracking solves each instances of a problem in an acceptable amount of time. Generate all the elements of the problem state. That's all. The remaining things I'll post it on the forthcoming video. Thank you.